Hi, in this video we'll talk about significant figures and then we'll talk about uncertainty. But before we start significant figures, in the last lesson we talked about measurement and we had some introduction about uncertainty. So in measurement, we have a measured value and we have the uncertainty. Um, so some apparatus, when they have a measurement, there are two uncertainties, the zero uncertainty and the judgment uncertainty. The zero uncertainty, like in the ruler, there is one uncertainty here, and the judgment uncertainty will be where we measure here. The other thing is reading, and in reading we have only one uncertainty. We don't have zero. There is no zero uncertainty, but there is only judgment uncertainty. The reason is because when they made this device here, they made it very careful and they avoided this um, zero uncertainty. Okay, this is what we discussed in the last video. Now, today we will continue and we talk about significant figures. Um, so, the first thing we will discuss the rules of significant figures. The first rule says that any non-zero digit is significant, and hence here we have three digits. All of them are non-zero digits. So we have three significant figures. This is the first rule. Non-zero digits are significant. Second rule, it says the zero. The problem comes with the zero. Zero between non-zero digits, they are significant. For example, 3.07. The zero in the middle here is significant, and hence we have also three significant figures here. Third rule, zeros on the left side of the first non-zero digit, they are not significant. For instance, the first non-zero digit is here. So on the left, these zero are not significant. The first non-zero digit here, the another example, is 3. So on the left, these zero are not significant. We look at this number over here. This number over here, 3090. We can summarize what we said here. The 0 in the middle is between the 3 and 9 is called captive 0. So it is significant because we said the second rule, zeros between non-zero digits are significant. So this 0 is significant. And the rest of the numbers are significant except this 0. This 0 is called trailing 0. Now if there is no decimal place here, the 0 is not significant. Okay. The other example is this one. So we have this 8 over here. This is the first non-zero digit. So on the left, the zeros are not significant. These leading zeros are not significant. And between the 8 and the 2, the 0 here is significant because it is captive 0. This 0 here now is a trailing 0, but it is significant. Why? Because there is a decimal point. Okay. Now let's move to calculation in significant figures. When we add or subtract the numbers, and when we say numbers here, means the measured value, and it means the uh, significant figures. Okay, significant figures. So we should round our answer, the result, to the same number of decimal place. This is a very important point. So let's uh, add these two numbers to significant figures. Okay, I have 256.5895 gram and I have 8.1. So my answer would be same as the number with the least significant figures, just like this, 8.1. So I will just carry out the addition. 5, 9, 8, 5 plus 1 is 6. I put my decimal place. 6 plus 8 is 14, carry 1. 1 plus 5 is 6. And then I will put the 2. So 264.6895 gram. So uh, my answer should be with one decimal place. But I have here, I have four decimal place. I have four decimal place. So what do I do to the rest of the numbers after the 6 here? So I will look at the next number after this 6, which is 8. If it is greater than 5, I will round. Greater than 5 or 5, I will round it. If it is less, I will leave all these numbers. So because 8 is greater than 5, I will round here. So my answer would be 264.7 gram. This is the answer after rounding. Let's go to the next. Okay, in multiplication and division, we should put our answer same as the number with the least significant figures, unlike the addition and subtraction. In addition and subtraction, our answer should be same as the number with the least decimal place. But here, it should be the same as the number with the least significant figures. And here, in this example, the number with the least significant figures is this one, 2.2, 2 sig fig. Okay, 2 sig fig. So this is L1 and this is L2. I want to multiply these two numbers, L1 times L2, to find the area. So when I multiply 2.2 times 38.2935, when I multiply this, my answer is 84.126900000. So and since my answer should have one decimal place, two significant figures, so my answer should stop up to here. And because this one is less than 5, I will leave all this. But if it is 5 or greater, I will round. So the answer is 84 centimeter. So the second example says 421.23 subtracted from 486. So I'm gonna put 486 here. Then I will put 0.00. Now I have to borrow from here. This would be 10. Again, when you borrow, this now is 9 and this is 10. 10 minus 3 is 7. 9 minus 2 is 7. This is now 5 because we borrowed 1. 5 minus 1 is 4. 8 minus 2 is 6. So the answer is 64.77. Now, the answer should be the number with the least decimal place. Here there is no decimal place, so answer shouldn't have decimal place. So I'm gonna look at this and round to here. So it will be 65. This is the answer. Okay, let's move to the next. Calculate and round the results. okay, to the same, uh, because this is multiplication to the same significant figure. Okay, so I'm gonna multiply the first one, 0.6238 centimeter times 6.6 centimeter. So how do we multiply this? Let me use a calculator. Okay, 0.6238 centimeters times 6.6. The answer is 4.11708. Now our answer should be the same as the number with the least significant figures, which is this two significant figures. So my answer should be up to here. What do we do to this? It is less than 5, we leave all this. The answer is 4.1 centimeter square. Let us move to the next example. Divide 421.23 gram by 486 milliliter. I'm going to use the calculator again. So 200, that's 400, sorry, 421.23 divided by 486. Answer is 0.8, 0.866. Then 7 to 8, and it continues. Our answer should be the same as the number with the least significant figures, which is the 3 significant figures. Our answer should stop here. What about this number? It's greater than 5, so I'm going to round. The answer is 0.867. This is the answer. Okay, let's move to the next. I'm going to put this file in the description part so you can practice these questions. Okay, now we move to uncertainty. So uncertainty can be found by two ways: from the device or from the range. We will see each one. So let's see the from the device first. How do we find the uncertainty from the device? So we will look at the least division or the smallest division or the smallest scale that the device can measure. Here the device can measure, you look here, up to 0.1. So the uncertainty will be half of this, 0.1 times half or divide by 2. So the uncertainty is 0.5. What about here? Look, this is 25, 26, 27, 28, 29, and then 30. So this the smallest scale here we can see is 1. Yeah. So half of this one. Half of 1 is 0.5. I beg your pardon. Pardon. It is here. Because it's 0.1, half of 0.1 is 0.01, 0.05, sorry. half of 0.1. We can calculate it on calculator. 0.1 divided by 2, answer is 0.05. Okay. All right, this is from the device. What if we don't have the device? We calculate our uncertainty from the range. For instance, in calculation, we have these readings. First reading, second reading, and the third reading. Different readings. So how do we find the uncertainty? So first we have to find the measured value. The measured value, we find it by the average. We add up all this, okay, the titer volume, okay, which is 48.0 plus 48.2 plus 48.4, because there are three values divided by 3. This is our measured value, 48.2. Now how do we find the uncertainty? From the range. How? The range is the highest value, which is 48.4 minus, and the smallest value is 48.0. So the range is the highest value, which is this one, minus the smallest value. Then divide this, because it is half of the range. Half of the uncertainty is half of the range. Okay, so divide by 48.4 minus 48.0, that is 0.4. Divide by 2, this gives you 0. Let's divide it. 0.4 divided by 2, that is 0.2. So plus or minus, this is the uncertainty. We said last time we put our uncertainty as plus or minus. So plus or minus 0.2. Okay, let's see how we can express the uncertainty. Uncertainty can be expressed by two useful ways. The first one, absolute uncertainty, just like in the previous example. This here, because it is the volume is centimeter cube, this is also centimeter cube. This uncertainty is called absolute uncertainty. Absolute uncertainty. Okay. So this is one mechanism. And as we said, if we have measure value, we don't have the device, just find the range and divide by 2. And the second way to express the uncertainty is percentage uncertainty. Okay. How do we find now percentage uncertainty? Percentage uncertainty is equal to absolute uncertainty divided by the measurement or the measured value times 100. So the percentage uncertainty, for instance, if the absolute uncertainty is 0.05 gram and the measurement is 23.25 gram, so I divide them times 100. That is the percentage uncertainty. Okay. Why do we need the percentage uncertainty? Because we might have uh, different units. We will see in some examples. But let's look at uh, this example over here. Okay. It says perform the following mass calculation. Okay. So we have 3 different measurements here. 1, 2, 3. With their uncertainties. 1, 2, 3. Okay. I have 3 different um, uncertainties. Okay. So first we carry out the normal maths calculation with the measured values. Okay. So 1.54 plus 2.5 1 1. So 4 plus 1 is 5. 5 plus 1 here is 6 point. 1 plus 2 is 3. So this is the first part. Then I will subtract from this minus 0.78. So I will borrow here. This is 5 now. 15 minus 8. 15 minus 8 is 7. And then I will borrow from here. This is 2 now. This is 15. 15 minus 7 is 8. So 2.87. This is the measurement. Now what about the uncertainties? I will add them, but I will not add them directly. I will use this formula to add them. Okay. U is equal to the first uncertainty square plus the second uncertainty square plus the third uncertainty square, all under root. So I'm gonna put my answer 0.2 all square plus 0.03 all square plus 0.02 all square. Now how do we add this? Let's use here. Okay, so under root square 0.02 all square plus 0.03 all square plus 0.0 all square. Okay, so when I use the calculator to find this, okay, let me use the calculator. The answer should be, this is 0.02 square plus 0.03 square plus 0.02 square. On the calculator, the answer shows 0.04. This is the uncertainty. So the final answer would be 2.87 gram plus or minus 0.04 gram. Okay. Can I change this to absolute uncertainty? Yes. How? Divide these two values. So 0.04 divided by 2.87 gram multiplied by 100. And this will give 1%. So final answer expressed in percentage uncertainty would be 2.87 plus or minus 1%. Okay. Now, so in addition and subtraction calculation, we should consider whether the result is just a single reading or a measurement. Okay. So if we have just a single reading like thermometer, in the last video we talked about this, we take only one measurement or measured value and our uncertainty is only one. But if it is a measurement, we would have, like in ruler, we would have two uncertainties. Or like this example, sample weight is equal to weight before minus weight after. So we would have here, for example, the uncertainty is 0.01. This is one uncertainty. And here we have another uncertainty 0.01. So we should consider this. Another example is this one. If the temperature rises from 22.6 degrees Celsius to 34.5 degrees Celsius. Okay. We want to find the change in the temperature. Okay. So our uncertainty is 0.1. Okay. So we have one uncertainty here and another uncertainty here. So we should consider this. Now we will subtract the measured values. Okay. For instance, it would be 34.5 minus 26.5 20.6. This would be 11.9. Now what do we do to the uncertainty? We will use the previous formula, that is uncertainty squared plus second uncertainty squared plus third uncertainty squared, and so on. We have two uncertainty, each one is 0.1, so it will be 0.1 square plus 0.1 square under the root. This gives 0.1. So my answer would be 0.1. This is absolute uncertainty. Let's change it to percentage uncertainty. So it will be 0.1. 0.1 divided by 11.9. Right? It's 11.9. Yes. Multiply this by 100. I'm going to use the calculator. 0.1 divided by 11.9. The answer is equal to there's the calculator. Multiply this by 100. So I should multiply by 100. 0.84. 0.84 and other numbers. But the least number is what? The least significant figure is one significant figure. So I'm going to round this. So it is 1%. So my answer will be 11.1.9 plus or minus 1 percentage. Okay, 1%. Okay, we move to the next. Okay, I will leave this to practice this exercise in the description description part. Like I said, I'm gonna skip all this. What about multiplication and division? So uncertainties in multiplication and division. Okay, we will add also the uncertainty. Okay, but we will use the percentage uncertainty now. We will use percentage uncertainty. So the first percentage uncertainty square, this is the formula, plus second percentage uncertainty square plus third percentage uncertainty square, and so on. For instance, if we have 23.2 centimeters square, and then we want to add to, we want to divide. Let me erase this. 23.22 gram, and I want to divide this by 200 milliliter. So in the uncertainty here, suppose it is 0.2, and the uncertainty here is 0.5. So what do I do? First, I have to change this absolute uncertainty into percentage uncertainty. How do we change? We said we divide and multiply by 100. So 0.2 divide by 23.22 multiply by 100. This gives, so 0.2 divide by 23.22.22 multiply by 100. Answer is 0.0.83. Okay, so I should have only one significant. Okay, I can round this to 1 percent. Okay, so the answer is what? For this one, 23.22 plus or minus 1%. Now I change it into percentage uncertainty. Let me change this also. So I'm going to divide 0.5 divided by 200 multiply by 100. Cancel these two zeros. 0.5 divided by 2. 0.5 divided by 2. It gives 0.25. But I can round it. So it will be 0.2%. 0.2%. Now I can add using what? Using this first percentage of uh, first uncertainty squared plus percentage of uncertainty, the second uncertainty square. And then I will put this under square root. So 1 over 100 all square plus 0.2 over 100 all square. This is how we can uh, add. Let's take example. Calculate the density of a liquid by measuring its mass. So the mass is 2.22 gram, and the uncertainty is plus or minus 0.05, and the volume is 1.414 plus or minus the uncertainty is 0.04. I'm going to normally divide. Density is mass over volume. So divide what? Divide 2.22 by 1.14. The answer is 1.9473. This is the answer. Okay, for this part. Now what about the uncertainty? So we said because there are different units, so we have to change the absolute uncertainty into percentage uncertainty. So let me use this slide. Let me clear this first. So I have two uncertainties, 0.05 and 0.04. So 0.05 divide by this to change it into percentage. 0.05 divided by 2.22, right? Yes, and multiply by 100. So let me use the calculator. So 0.05 divided by 2.22 multiply by 100. Answer is 2.2, and then it continues, but the number with the least significant figure or the least decimal place is this. So I'm gonna drop this, so it is 2%. So my answer is 2.22 plus or minus 2%. Let's move to the second one. Second one is 1.14 and 0.0, the uncertainty is 0.04. So I'm gonna divide. Let me divide here, clear this first. So 0.04 divided by 1.14 multiply by 100. So 0.04 divided by 1.14 1,4 multiplied by 100, 3.5, 3.50, and then it continues. So I will round to have one decimal place, that is 4%. So the answer is 1.14 plus or minus 4%. So now we divided this and we got an answer earlier as 1.947, 1.9473, and so on. So we will add this in the formula. First percentage square, so 2.2 divided by 100 because it's a percentage, all square, plus this is also percentage, so 4 divided by 100 all square. When I carry out this under the root square, 2 divide 2 divided by 100 all square plus 4 divided by 100 all squared, okay, and all this under root. So the answer would give 4.4, and then it continues. So because this is less, I'm going to drop this. So the answer is 4%. So my final answer is plus or minus 4%. So this is how we carry out a math calculation. So the final answer is what? 4%. So can we change it back into absolute uncertainty? Yes, we can change it back into absolute uncertainty. How do we do that? This 4% divided by 100 because it's a percent, and then multiplied by the value, which is 1.947. So when you multiply this, you would get 0.08 gram per milliliter. But I will not take all this answer because the answer with the least sig fig is 3 sig fig. So what do I do to this? So up to here, yeah, 3 fig. I'm gonna round to here. So the final answer would be 1.95 gram per milliliter plus or minus 0.08 gram per milliliter. That's the final answer. Next, we're gonna discuss another topic, accuracy and precision. What is accuracy and precision? Okay, when we measure our measurements, we take measurements. Okay, if our answers are close to the target, so this is the target or the true value. Okay, suppose it is 22.3 centimeter square. If our answer are very close to this true value, we are accurate. And if all our measurements, suppose we are repeating the experiment 3 times, and in the 3 times, okay, we are measuring first 22.2, and then 22.1, and then 22.3. So all our measurements are very close to each other. So we are precise. So being accurate is when our answer is very close to the true value, and being precise when our all measurements are close to each other. Look at this one now. Here we are precise because all our measurements are close to each other, but we are not close to the true value. So we are precise but not accurate, because we said we are accurate if our measurements are close to the true value. What about here? Here we are not precise because even our measured values are not close to each other. So we are not precise, and we are not also accurate because our measurements are not close to the true value. Thank you. See you in the next one.